Okay, so today we have lecture 6 still about diffusion. So maybe you remember that the main purpose of our previous lecture was introducing multiple species in our simulation. So however, at that time our two dopants, p-type and n-type, were not interacting to each other. So today we will talk about what will happen if they are interacting through the electric field. So yes, the first thing is when we consider diffusion, at the first time we neglect the electric field. However, in principle, since our dopant atoms are ionized, so they are affected by the electric field. So we must consider the terms called as diffusion. So previously we had flux only considering diffusion term. However, now we have to consider the term like this one. Here we have a second term. This is corresponding to the drift mechanism, and drift means that the motion of our dopants, like a positively charged ion or negatively charged ion, by the applied electric field. So here we have two different directions of our velocity, drift velocity. When our particle is positively charged, then now we have the aligned direction of our dopant ions with respect to this electric field. However, if we have a negatively charged dopant ion, then although electric field is applied to this way, but negatively charged our dopant ion, so for example boron, can move in this direction. So please note that we have a difference of polarity due to the different charged particle. Okay, so this is the form, the original form we will use. However, when we just insert it, then let me just write down the flux of our dopant C can be written as so usual diffusion term, and also sometimes we have C times mu E, and sometimes C times minus mu E. So it is very inconvenient to write down the same equation with only slightly different sign. So instead of that, why don't you just write down this way? So please note that when we write down in this way, we assume that the upper one, for example positive sign in this case, is for positively charged dopant ion, and this negative sign is on the other hand for negatively charged dopant ion. So once we accept this kind of notation, then everything is just merged, so we can reduce the space. Okay, so quite convenient. So instead of write down all the way around, then just to introduce two cases, one expression. So now we wanted to implement this one. Wow. Here we have electric field. However, with the electrostatic potential, so also under the electrostatic potential approximation, then we can write down in this way. Okay, so electric field can be written as just a gradient of a certain scalar field called the electrostatic potential phi, and here we have a negative sign due to our convention. So please note that electric field has the direction from higher electric field, high electrostatic potential to low electrostatic potential. So when potential is high and low, then there will be the electric field. So simply speaking, here you have a region where you have 3 volt, and here you have a 2 volt region. Then what is direction of your electric field? Obviously, you have the direction of this way. So when you just take gradient of phi itself, gradient itself is try to give us the direction of maximal change, maximal increase. So the direction should be this way, because following this path, then you will find that your phi value is increased most rapidly. So in order to match our electrical fields convention, then we have to introduce minus sign. So then what will happen? If we just adopt this one, then we can simply write down in this way. The diffusion term is not modified at all. However, this electric field term can be written as minus plus because of this negative sign, and here we have mu times c times this one. Please, once again, I wanted to let you know mu is mobility. So sometimes people say that mobility and mobility many times. However, in this case, this mobility is mobility of a dopant ion we are talking about. So later in this course, you will have also many different mobilities. For example, mobility of your electrons and mobility of your holes inside the silicon substrate. So compared with these electron and hole mobilities, so this mobility of a dopant is extremely low. So electrons can freely move, but in the case of your dopant does not move quite fast. So that's the reason why you have a quite low value for your mobility. Well, anyway, now you have much better form, but still you have two different terms and two different coefficients called diffusivity and mobility. Well, in general, they are different, so they should be different quantities. However, we adopt the Einstein relation. So here the Einstein relation means that diffusivity and mobility are linearly proportional to the summer voltage. So that is the Einstein relation. So first of all, think about the unit of diffusivity. What was the unit of this diffusivity? So it was some length scale squared divided by second. So that was the value. And what was the unit of your mobility? Mobility as the unit of square centimeter divided by volt and second. So you can immediately understand, although they share the same dimensions, but one is missing. What is missing is here you have 1 over V, so voltage unit. So when you apply or multiply this voltage unit, then you can find that there is correspondence of their unit. So no conflict here. And now this is Einstein relation. But I want to say that this Einstein relation is not a general relation in a sense. when you consider general cases, you cannot actually assume this Einstein relation. So, but it is generally valid when you consider equilibrium cases. So, equilibrium cases, it is always true, and non-equilibrium case, there is no guarantee that we have the Einstein relation. So, what we assume here is, okay, our system is not exactly at equilibrium, but deviation from the equilibrium would not be very large. So, although this is not perfectly equivalent, but why don't you just say that, yeah, this is just our approximation. Why? Without this approximation, then we cannot go further to simplify this equation. So you are now talking about the field called as process simulation. So in this process simulation, we are talking about how can we simulate the fabrication process. Later in this course, you will consider also device simulation. However, interestingly enough, even in that case, you will find that we are heavily relying on this Einstein relation. Although Einstein relation is not actually applicable to the general cases in non-equilibrium case, however, we still use in both cases, process simulation and device simulation, the Einstein relation. Okay, so are you with me? So we have to understand our limitation. Then here I wanted to say that what is summer voltages? To some of you, summer voltage is quite a familiar concept, but to some of you, maybe not. Summer voltage is given by just kVt. So when you have just kVt, this is energy. So this is a Boltzmann constant and your absolute temperature. So it will give you a quantity corresponding to the energy. And here you need a voltage quantity. So obviously they are different. So by dividing this summer energy uh, by our unit elementary unit charge Q, then we have the voltage unit. This is the value. This is the expression for summer voltage, and maybe it is good to know the value at 300 Kelvin. So what is it? Anybody? Do you have any idea about the value of a summer voltage at 300 Kelvin room temperature?
600.
Okay, so good. So my memory is like this. So yes, roughly you can say that 6. So please, but of course in general, when you actually implement your code, please do not use these approximated values. So even for me, I don't remember the Boltzmann constant exactly, but when you write down your code, please your exact kb values, so then you can have good number. Okay, well, anyway, thank you for your answer. So since this number is just proportional to the absolute temperature, so simply speaking, if we have 1200 Kelvin, then what will happen? So that will be the summer voltage quite close to, so 0.1 volt. Okay, so this is just linearly scaled by the temperature. Okay, so then when okay, it is now also stuck, so we have to wait for a while to be restored. Okay. I do it is sometimes stuck here. Well, anyway, if we adopt this kind of thing, then our mobility can be eliminated from our formulation. How can you do that? So just to insert this form. Mu is d divided by our summer voltage. Then, now you will find that our form can be written as this way. D divided by summer voltage. Wow. Then what happens? Now we have a common factor. What is it? Common factor D, diffusivity. So now we can collect them all. The way is take minus D, then we will have gradient of concentration and positive, negative, and 1 over summer voltage and C times gradient of phi. So that is exactly the same shown here. So do you have any question about my derivation? So starting from very obvious expression for the flux with diffusion form, then I have introduced electrostatic approximation and Einstein relation. Of course, which one is weak or just approximation and which one is quite acceptable? This one, electrostatic approximation, is quite good. However, adoption of this Einstein relation, yes, this is questionable, but however, we have done it. Then we finally arrive at this point. Well, yes, so if we know the value of C and phi at every node, then we can calculate the gradient and its gradient. Then we can also calculate these two terms. But who give you the answer for electrostatic potential? You know, this concentration itself is our unknown variable. So once we try to calculate our diffusion equation, then since it is the unknown variable itself, so by solving the diffusion equation, we will understand what is the value of this C. But who give you the value of electrostatic potential? So unfortunately, it is not available from the diffusion equation itself. So there is many different ways, possible different ways. One is, most rigorous one is just to solve the Poisson equation. So what is it? I will explain later. But today, instead of that, we will try to make a simple estimation for electrostatic potential in terms of our unknown variable C. So then, now you understand my strategy. So here, flux is, previously the flux was written as just constant D and gradient of C. So this is quite much linear to the concentration and it was easy to discretize. So now we have the additional term, but it has two terms, C and yes, C is also another, once again, unknown variable, but here we have phi. Phi itself is not known to us. However, by saying that, okay, even the phi is modeled as a function of concentration, then eventually our form shown here can be written as the flux, which is a function, or which can be written as in terms of our, I made mistakes, sorry about that, function which can be a in terms of only capacity. Oh, sorry, what is it? So concentration. So in this semester, I'm doing 2 lectures, so sometimes my terminologies are mixed up. Okay, so now let's go to this page. Then how can we express this phi? Then what happens? So in this work, we will just assume the equilibrium case. So please note that this is a real assumption. So when you actually do the process, semiconductor process, and when you fabricated your device, actually your system is not in the equilibrium case. Your dopants are moving and your electrons and holes are moving. They are all moving and not in the equilibrium. But here I'm saying that at equilibrium, then how can we justify our assumption of the equilibrium? So are we completely wrong or not? This can be justified by the time scale of 2 different systems. So please note that when we have vapor, and we are now talking about the motion of positively charged ion and a negatively charged ion, and motion of electrons and motion of also holes. And you know that 2 of them are ions. Yes, this guy and this guy are ions, and 2 of them and mobile carriers, this guy and this guy. Then think about their motion. Yes, although we are trying to move these 2 atoms, but its time scale is like a second or minute or hours. And how about the time scale of their movement, electrons? Maybe their movement can be obtained in a picosecond or nanosecond, even microsecond. Okay, so when we think about these 2 things, so severe distinction of time scale here and there, then when this atom, slowly varying atoms within 1 second, slowly, then almost immediately this electron and hole will move according to the local or temporal equilibrium cases. So although, so from the viewpoint of these dopants, they are not in the equilibrium case, but under the given dopant concentration, we can assume that these electron hole pairs are in the equilibrium. So that is one thing we can say at equilibrium approximation. Then in this case, actually only in this case we can write it down. So now electron can be written as the function of our electrostatic potential. So are you with me? Of course, this one has also another approximation like Boltzmann statistics, but you know, we are talking about not 300 Kelvin, or we are not talking about 77 Kelvin or 400 Kelvin. So in the case of low temperature, actually, no, it is very important to consider exact statistics for our electrons. So Fermi-Dirac distribution is quite much required, especially for low temperatures. However, what is the temperature of our interest? Now you are talking about around 1000 Kelvin or even higher. So in this case, now you have a quite much elevated temperature. In this case, Boltzmann statistics is not that bad, so you can write it down in this way. So simply speaking, now in this case, you can just invert them. So this n is written as a function of phi, but now our phi can be written as function of n. So you can take just log in left hand and right hand side, then you can easily obtain this form. Then from this form, please take the gradient. Then what will happen? On the left hand side, you will have gradient of phi, and your right hand side is gradient of Vt log n over an intrinsic carrier density. And in this case, we assume that temperature is constant over our vapor, so we can put it down here. And yes, this is quite much available to you. So now gradient of phi, that is actually driving force of your drift term. So once again, here you have driving force corresponding to the concentration gradient, and here you have another mechanism called drift, which was driven by the gradient of your electrostatic potential. What is the gradient of your electrostatic potential? Nothing but this is electric field. E field is shown here. Now your E field can be written as just a gradient of your log of your electron density. So you know this is still constant, so when you take the gradient, this term doesn't contribute to error, but here you have electron density which is really position dependent. So do you have any question up to now? So you can find that we are now introducing some approximations to reformulate our equations, but still many of our approximations are quite much reasonable. So up to now we have done reasonable reformulation for our flux term. So previously when you had just diffusion term, obviously there was nothing, and only when you consider the drift term, now you have this additional term. Okay. Then now you will have this form. What is the difference between this form and that form? Yes, I just take the shared one, C. So now here you have C. Now you don't have C here, but since it doesn't have C here, so now we have to have terms like gradient of C divided by C. You know that this can be well written as gradient of log C. So are you with me? So this is quite easy. I mean that dx of log y can be written as y of, yes, so once again dy dx. This is already known to you, so that's the reason why we can make this form. Well, then please make a comparison with your reformulated form and your original form. What is the difference? Previously, when you had the original form, it looks like this. terms, you must take the gradient of certain quantities directly. And now please have a look at here in this term. Now you have the common factor here, and your gradient is taken for the logarithmic of your concentration. Why that is so important? So think about this one. Maybe you remember that our previous homework number 3 or something like that was about the diffusion between 10 to the 20 per cubic centimeter, and another one was 10 to the 17, if I remember correctly, per cubic centimeter. And when we had this kind of severe changes, so what will happen? So of course we have straight line. Yes, in this case, since we have not considered any other effect, this is really a correct one. But what I wanted to say is, in reality, when you try to solve a realistic problem, such kind of a huge difference of concentration, C equal to 10 to the 20 and C equal to 10 to the 17, can happen quite frequently. So now maybe you may find that dopant density varies quite rapidly than this linear like discretization. So I mean that this one is not that good. Although I mean that in analytic sense, let me just follow. This one can be easily written as this one. Do you have any objection on it? Of course, we believe that C is a positive number, and also we will reformulate it as this gradient over log C. So if you have any objection on my formulation, then please let me know. They are equivalent. Gradient of C is equal to C times log C. But please note that when you just consider this form, then what you have to do is, okay, C over xi plus 1 minus C over xi divided by delta x. And when you take this form, then you have a certain C values. What is it? We have no idea. However, the gradient shown here in the one-dimensional case can be written as delta x, and here we have log C over xi plus 1 minus log C xi. So what's the matter? The matter is here, this one and this one. We are now taking the difference of our concentration itself. It is quite rapidly varying. However, even for this case, for rapidly varying concentration, when we take the log, its deviation can be much more reduced, and our assumption here can be much better than that, better than this one. So this is the typically used form for our diffusion equation in reality. Okay, so although in analytic sense there is no preference between this first form and second form, they are equivalent. However, point is we are not solving this equation in an analytic way. We are solving this equation in a numeric way. So then we have a certain preferred way for discretization. So certainly this is the way we do in the case of process simulation. Of course, I wanted to say that then how about our device simulation? So are we also taking this kind of thing? No. In the case of a device simulation, we have also its own discretization scheme. So we will consider it later. But for a while, so in this scene, so we will just take this form. And the beauty of this form is also it is quite general. So although we have introduced a new term, it is just added, and it has also quite a similar form like taking log of C and taking log of electron density. So they can be written in a unified form. So we will use this form. Okay. So up to now we have covered to here, and now we will make some discussions on our system or our discretized problem. Okay, so do you have any question on my explanation? So if you have any, then please let me know. I will be happy to answer your question. So now looks good, but it was all just a reiteration of the same problem. So although we are now having more suitable form for discretization, but nothing happens. Still, my question is, what is n? Who decides the n? Previously, I asked you the question, who decides phi? At the time, no answer. And now, still, who decides n? Still, we have no idea. So, once again, in a rigorous sense, we must calculate n. It means that in order to calculate n rigorously, then we have to introduce another equation for electron. Because you know why we must solve the diffusion equation? Because we wanted to know this evolution, time evolution of this concentration. Then we need another quantity. If you really wanted to know the n density, then you have to introduce a suitable equation for n, electron density. So if you have two unknown variables, then you need two equations. If you have three unknown variables, then you must introduce three different equations. That is the rule. So you cannot generate three unknown variables out of only one single equation. This is not possible. If you have one thing unknown, then you need the corresponding equation. So I mean that when we try to calculate the n value, then we must introduce another equation, and that equation later we will find that this is corresponding to the so-called Poisson equation. However, you know, solving the Poisson equation really costs quite a lot. So instead of that, in this part, so I mean that not in general cases, but in this lecture, we will use a specific assumption. This is the real assumption. Is it really correct or not? It's not, unfortunately. Even at equilibrium, even when we assume the equilibrium, this approximation called charge neutrality is not valid at all. So this is the pure approximation, and our solution obtained from this charge neutrality condition would not be good enough. Please note once again the limitation. But you know, I want to say that we have introduced many different approximations. However, this charge neutrality approximation is the most severe one. For example, what we have done was introduction of a triplet. It's okay. Electrostatic approximation, it's okay. And Einstein relation, when we assume the equilibrium case, then it's perfect. However, it's not actually. Our dopant diffusivity and dopant mobility can be a little different, but it's just okay. So we can accept this rule. And let's go. Another approximation was the equilibrium condition for our electrons. In my opinion, it is quite okay due to the different time scale and due to the highly elevated temperature. So it's okay. And yes, what else? Now we have the charge neutrality. However, unfortunately, this charge neutrality is the real approximation and no justification at all. So please note that this is the real approximation. I mean that if we stop here, okay, then let's try to calculate the n using the Poisson equation, then I will be happy with it. However, in order to make things simple, then we have introduced the charge neutrality. Then the calculated electron density is not the, the real solution, so we must care about this one. Then what is the reality? For example, actually you can buy the process simulator. So it takes some money, but still you can buy it. Then in your actual commercial process simulator, what will happen? It provides two different options. For example, this option, charge neutrality option, is also available. Why it is available? Because it accelerates your simulation. And also you have another option, more slower options, like solving the Poisson equation rigorously. So both of them are available and both of them are actually used in the realistic cases. So once you accept the limitation of this charge neutrality, then I will start the discussion on it. So charge neutrality simply states that everywhere in your device, everywhere, the net charge density is 0. So in the left hand side, you can find the total number of positive charges. And in the right hand side, you can find the total number of negative charges. So you know that positively ionized donor and also holes can contribute to positive charges, and negatively charged acceptor ions and electron can contribute to negative charges. So once we have this kind of condition, charge neutrality everywhere, then yes, we will have just constant electric field everywhere, because so our Poisson equation just state that actually this is not Poisson equation in our conventional form, but this is a Gauss form. So when we have this form, actually this law is local charge density, and this charge neutrality condition means that yes, this local charge equal to 0. So now we will have this form. Simply speaking, then there will be no gradient change of the gradient or a change of a divergence in our electric field. So this is a displacement vector. However, it can be well expressed in terms of electric field. So divergence of electric field will vanish in the case of our charge neutrality condition. Okay. So is it realistic or not? Certainly not. This is quite a bad approximation, so don't believe it. So it's not. Actually, in the case of a device simulation, you will use this charge neutrality approximation as a starting point of your analysis, and you will find that your final solution is far much different from this charge neutrality approximation. So this is a really poor approximation. However, unfortunately, we have no better way to approximate something in a local sense. That's the reason why we are talking about this one. I'm stressing that it's not perfect. But anyway, once we accept this one, then here we have a second equation, like a product between n electron density and hole density is equal to square of intrinsic carrier density. Also, this is valid only at equilibrium of electron hole system, but we are already assuming this equilibrium condition for electron hole system, so we can combine them. Then what will happen? Let me do it. nd plus minus na minus plus p equal to n. Easy. And by using our second equation, then we can write down n intrinsic carrier square divided by n is our p. And eventually, when we multiply n in left hand side and right hand side, then we will find that square. And here we have n. That will be the equation for our electron density n and second order term, so quadratic term and linear term and constant term. So also you know the formula for the solution, and it is written in here. Okay, so now you understand what it is. So now talking about this one. Now you have a homework. Your homework number 1 is like this. In order to calculate the electron density under the charge neutrality condition, you have to know this doping concentration and doping concentration. Let's assume that you know the doping concentration. Then what happens? Can you calculate the electron density? If you know the lead circled one, then can you calculate the electron density following this solution? You cannot, because here you have another term related with the intrinsic carrier density. So intrinsic carrier density should be known, and in this homework problem number 1, the intrinsic carrier concentration in silicon is written as here. Okay, then please try to evaluate it. When you apply 300 Kelvin, then you have to have intrinsic carrier density, which is orders of 10 to the 10 per cubic centimeter. So first of all, please check it. And yes, once you calculate this intrinsic carrier density at a given temperature T, then now following the solution here, when you have doping density and intrinsic carrier density at a given temperature, then now you can consider the electron density at a given temperature. So simply speaking, this N can be a function of doping density, net doping density, and temperature. My question is, in the problem 1, I give you these values and these values. Please follow this formula just to evaluate it. It is not a level of graduate student, but anyway, please follow it. Then temperature ranges in the absolute temperature starting from 300 Kelvin room temperature, and this number quite close to 900 Celsius. So this is a typical our operating temperature for our summer annealing, and consider 3 values of doping concentration. So here we have 3 different values. Then what I wanted to ask you is like this. As a function of temperature, you increase the temperature from 300 Kelvin to 1200 Kelvin. Please calculate your electron density. Then you will have 3 curves. Why do you have 3 curves? Because N is function of doping density and temperature. And now I'm asking you consider 3 different cases: 10 to the 20, 10 to the 18, and 10 to the 16. Please do it. Then you will find the variation of your electron density as a function of temperature. Okay, so are you with me? So please draw it. So although this is quite simple, but it will give you what is important temperature range and doping range for your concentration. I mean that, let's say that since we are talking about a new flux term here, our interest is laid on this second term. So we wanted to find out where electron density varies quite severely. Let's say that if this is constant over our vapor, then what will happen? If this is just a constant, then this term will not contribute to our flux. So this is meaningless. However, if we have severe dependence on N, severe variation over N, then that will make some dependencies. So simply speaking, here we have N, and this is once again function of concentration and temperature. And when we have severe dependence of electron density on the doping density, low temperature or high temperature, I'm asking you this simple question. So secondary term is related with drift effect, so electric field related effect, and is it severe at low temperature or is it severe at high temperature? That was my question, and you can now answer my question by solving this homework number 6. Then you will find that okay, which one is actually important temperature range. Okay, so please, although that is quite simple, then please do it. Then now let's try to discretize our flux term. So here we have the original form written in terms of gradient of some quantities. So this gradient can be applied to 1D, 2D, and 3D cases. But if we just restrict ourselves to the 1D case, then this gradient becomes just a partial derivative with respect to position x. Why do we have it still partial derivative? Because in this system we have also the dependence on time. So that's the simple reason why I just use partial derivative here. Then now we ask this question: how can we discretize the flux? Now discretize here means that how can you treat this derivative and this derivative term? It is not that difficult. Let's just say we are now considering the flux between xi and xi plus 1. Then how can you do that? So this gradient term can be written as 1 over delta x and difference of log c evaluated at xi plus 1 minus log c xi. This is the first term, diffusion term. And the second term comes in here. Also, electron density is evaluated at xi plus 1 and electron density is evaluated at xi. Do you have any question? Here you have a little bit complicated signs here. However, you know that this is obtained from just having the sign or negative sign or inverted sign for here, because we must take the first term and it's inverse, so we have this form. Any question up to now? Well, however, there is one hidden point we have to discuss once again. Yes, it looks perfect. Now we follow the rule we have done up to now. We were successfully able to discretize it. But here we have C. And here we have discretized C. What should be the form of C? Here, our C is written as C evaluated at xi, C evaluated at xi plus 1. Of course, since we are evaluating this flux, the range between xi and xi plus 1, so maybe this C is corresponding to C at maybe the midpoint between xi and xi plus 1. Then how can we calculate these C values defined at midpoint? Actually, C at xi or C at xi plus 1, they are available. They are solution variables, and even in the discretized form, we know them as a solution vector or entries of our solution vector. However, in this case, we have no idea. We must make a clever guess on this midpoint quantity. So in this case, now we take just this form. Simply speaking, it means that C is exponentially changing. If C is changing linearly, then maybe better idea would be like this: xi plus C xi plus 1. This average will be better for linearly varying quantity. However, if the quantity is exponentially varying, then this one would be better. So we will use this so-called logarithmic flux approximation. So this term will be used. Then is it the best one? Actually, in the 90s or 80s, so several decades ago, people were very interested on this stuff, and they invented many different ideas on it. And I wanted to say that this is not the most accurate one. It introduced certain error on our discretized flux, but this is easy to implement. So in this semester, we will rely on this expression. So this is main contents of our today's lecture, and now we must understand it's not that easy situation, because now it means that our newly invented flux term is written as the function of Cxi and Cxi plus 1. Good. This one here, this one here, and this is constant, and similarly this is constant, and here we have also C, and here also we have C, and even this N can be written as the function of our C. How can you do that? So here we have the expression for our N. So doping density determines electron density. So well, that is not that straightforward, but eventually we can calculate the electron density when all dopants concentrations are available. So in principle, we can evaluate this from the flux once we know the dopant concentration everywhere. But why? Why I'm talking about the difficulty of solving this system? It is because although it is f sub c can be now written as in terms of c, but this is a nonlinear expression. So let me just go to the second topic here, nonlinearity. So now let's try to solve it. We have invented a better flux term compared with the previous one. Now we have a much better one. So now you understand this guy is actually corresponding to the integrated time derivative term. Now you understand. And this right hand side term is actually corresponding to, once again, integrated your flux term. Yes, now you understand. So this is quite general. Even when we have a better or worse flux term here, or good or bad flux terms here, that doesn't alter this form. This form is quite general, and when we modify, when we update, when we improve these FC terms, then the specific form of these fluxes will be changed. And previously we had a simple form, and now we believe that when we consider drift effect, then flux terms can be written as this form. So this is just a copy and pasted version of our previous flux. Okay, so looks good. So now you can evaluate this equation. Wow, here you have FC evaluated at between xi and xi plus 1. you need another flux evaluated at xi and xi minus 1. Then you can also easily write down xi minus half corresponding to the midpoint between xi minus 1. You can do it. Evaluation itself is okay, but my question is shown here. Is it a form of ax equal to b? Can we make the matrix for A? So when you make a certain matrix and when your solution vector is just C, then when you evaluate this ax terms, then what you get is just a collection of many equations, and these many equations are just something multiplied by c, something multiplied by c, and something another one multiplies c, blah blah blah. That will be the form you can generate from this matrix vector multiplication. You cannot generate, for example, can you generate this squared c term out of this ax multiplication? Of course, if you want to do that, then you can insert here c, but this is really against to our philosophy. We are not doing this kind of thing. We wanted to have well-defined A matrix which has fixed element given numeric elements. Then we wanted to take the inverse of our matrix A. So it's not possible. Always this preferred form Ax equal to B gives us just a linear combination of our unknown variables. Unfortunately, here the flux term shown here is not available to be expressed as a linear combination of our solution variables. That's the problem. You can easily understand the difference between our current problem and previous situation. Please have a look at this one. Recall our previous case. In our previous simple diffusion problem, the discretized equation, diffusion equation, had this form. You know, this was related with flux C, and this one was related with another flux C. And you know that the flux term can be written as the linear combination of your solution variables. Also, previously your flux term was able to written as linear combination of your flux terms. So that was linear to your solution variables. But now, it's not. So therefore, right now, you cannot generate your matrix A. Therefore, our obvious conclusion in this lecture is when we consider more realistic problem, we always be encountered to the non-linearity. Non-linearity is the key difficulty to be coped by our effort, and at present we cannot solve the problem, this problem shown in the previous slide, because it is nonlinear. So now we have to understand how can we solve a non-linear system. That is really key point. So yes, so actually solving the nonlinearity or solving the nonlinear problem is the central problem of this computational microelectronics, because every realistic problem is nonlinear in this field. So please note that solving nonlinear problem is really important in this work. So since the time is up, so I will just stop here. Although I have prepared another uh, another homework number 2, but I will just cancel it. So please do your homework problem only one, and yes, next Monday we will keep the discussion about how can we solve these nonlinear problems. Okay, do you have any question about our lecture content today? Okay, if not, then let's wrap up today's lecture. Thank you.